and thank you everyone for joining our webinar. It's a great pleasure, and today I'm going to share our recent research on unlocking brain health through multimodal digital twins and three-dimensional vision foundation models. So first, I would like to give an overview of the research in my lab, which sits on the nexus of artificial intelligence, neuroscience, and brain health. Well, we first use neuroscience principles to build brain-inspired AI systems that are more efficient and intelligent, just more like human or primate brains. And then we use AI as a nearly costless and efficient platform to test neuroscience hypotheses that are impossible or very costly before. And on the other hand, which is more relevant to today's talk, is we use AI to empower brain health, where we build AI systems that can perform early diagnosis and precision intervention. And then we use the domain knowledge from the brain health space to build better AI in turn, because we want to make those AI systems more trustworthy, explainable, equitable, and also personalized. And because of the interest of the audience in today's talk, I will focus on the second part of research in my lab, which is AI-empowered brain health and health-driven AI. Today's talk will be on how we unlock brain health through multimodal AI, where we build multimodal digital twins as a bottom-up approach because we want to have the nitty-gritty of different details of how the brain works in a in silico replica so that we don't need a patient to experience all the intervention or drug to know what will be the treatment outcome. So you can see how this is a bottom-up to model the human's brain. And then we will also introduce foundation models in 3 dimensions as a top-down approach, because we are going to use massive data sets to train a 3-dimensional foundation models for the human brain. And then we can use it in zero-shot or few-shot learning for the downstream tasks to solve different brain health challenges, such as segmentation, disease diagnosis, and prediction of the future. Let's first look at the digital twin part. Did you know that 40% of the worldwide dementia could potentially be prevented or delayed by targeting modifiable risk factors alone? And those risk factors include things such as physical inactivity, less education, lack of social contact, and also depression. So there are different ways actually we can prevent or slow down the progression using some training or intervention, such as cognitive training, which you can see as a game for the brain, where we can improve the working memory using card shark or auditory ache or memory grade, and processing speed using double decision, all those different types of games in, for example, the NIH toolbox. And very long-standing clinical trials have shown that cognitive training can improve the cognitive abilities such as working memory, executive function, and daily living function in older adults, even with a 10-year lasting effect. And when it's paired with a non-invasive brain stimulation method called transcranial direct current stimulation, or TDCS, it's hypothesized and showed in the phase 2 clinical trial that the effect of the cognitive training could be improved because TDCS is hypothesized to change the electrical field and the neuron resting membrane potential so that the neurons are easier to fire, and also it can change the neuroplastic response of tissues and the functional connectivity. However, the response to cognitive training paired with TDCS is not always homogeneous. Based on a large meta-study published in the past 4 years, you can see that the overall effect for working memory only has 0.48, which is a moderate effect size. And for all the cognitive domains, it has 0.63. And this is because when we apply the TDCS to the human head, we have to put electrodes on a certain location based on the EEG 1020 montage. And usually they are put on the F3 and F4 locations for the anode and cathode and at a fixed electrical current level of 2 milliampere. But does it work for everyone? Can we actually target exactly the same brain regions at the expected electrical current level when we apply the same montage of stimulation for everyone? I think the answer, you can guess, is no, because everyone has a different head anatomy, especially for older adults. They have different level of brain atrophy. And just for everyone, the skull thickness and adipose tissue distribution are different. And all those will impact the current distribution in the brain because of the different tissue conductivity for the current and their heterogeneous distribution. So to address this issue, we propose to build a multimodal digital twin where we can map the physical patient or participant to a digital replica in the computer. And basically, we want to use a deep neural network to implement this mapping. And in addition to the imaging, we can also integrate clinical history, analytics, lab tasks, and DNA sequence, which are on the horizon for some of them. But we have already got very promising results and published them by using the multimodal neuroimaging data. So what is the brain digital twin? From the inspiration from Nina, a brain digital twin is a digital model of a physical brain that serves as its effectively indistinguishable digital counterpart for scientific and clinical purposes, such as treatment planning. For example, if my brain has a digital replica in the computer, then if we want to apply any intervention or try the different drugs or the different level of hormone or the different stimulation in TDCS or TMS, the patient or the participant or me don't have to go through each different combinations of intervention or drug, but we can use a digital twin to directly and in silico test what will be the treatment outcome, and then choose the optimal outcome for this specific individual. Wouldn't that be a dream come true for the clinical trials? And before I dive into how we perform the digital twins for the brain, I want to give a little bit overview of the history of how the brain replica develops over time, including the brain atlases, brain templates, and the brain digital twins, so you can have a better understanding of the landscape. So brain atlases are actually a neural map which defines discrete brain regions, which can be seen in this colored map. And each region represents important, for example, cortical regions for a specific function. However, this is discrete and does not represent the whole brain in continuous space. And brain templates represent the average typical screen brain in a more continuous space because for every pixel, we have a unique value. However, you can see that the resolution for those brain templates are usually not very high because it's an average of, for example, MNI 152, you can see from the name, it's an average of 152 participants. So it's basically trying to use one average model to represent all the population so that we can morph individual brains to a template to perform further analysis in a more normalized space. But that cannot represent individual person. And here, the brain digital twins is a replica of one brain to test hypothesis. And this is not trying to say we are trying to use the average person to say how this drug or a certain intervention will respond. We want to look at the exact specific individualized brain anatomy, functional connectivity, as well as combined with clinical characteristics and features to test if we put intervention, for example, on this toggle bar. I can put TDCS stimulation intensity in the current from 2 milliamp per second to 3 milliamp per second, and how the brain will respond. This is what a digital twin of the brain represents. And to build a digital twin of the brain, we will first start with a human brain, and then we can have multimodal data, for example, T1 and T2 flare MR. And now we are also working on the resting state and task functional MRI to be integrated. After that, we will perform a fundamental step, which is head tissue segmentation. Even segmentation is so well studied. It's not really available in a real time, and also for all the different tissues which have different tissue electroconductivity. And then we can input or test a TDCS stimulation montage hypothesis, for example, between applied intensity of 0.1 to 4 milliampere. And then there are also 71 possible electrode locations, which comes up to about 5,000 pairs of combinations of anode and cathode. So in total, there are about 200,000 potential TDCS montages or doses. So when we build a digital twin, we don't have to do this on one individual person who will be so poor if we have to do that on the participant. And then after we have this montage and the head segmentation, we can perform volume measurement and finite element modeling to get the electrical current map in the brain. And those finite element modeling methods have been well validated in animal and human models, so they are quite accurate and well accepted in the field. And after that, we can have a digital replica in the computer where when we change the stimulation parameters, actually we'll have the JMap in this digital replica. So in this way, we can map the human brain to a digital brain, and we can build it in minutes or even seconds at times. And to put this into a perspective of the engineering roadmap, this is how we perform all the steps in this R01 funded project. And this effort cannot be completed, or some are still in the process, without my excellent and wonderful collaborators and my students in the Smart Lab. So we'll start on this roadmap with a segmentation. So as I said, even though segmentation is a well-studied topic, older adult segmentation on such a large phase 3 clinical dataset with 379 participants have never been done into 11 tissues. The reason why we want to segment the whole head into 11 tissues because each tissue have different conductivity value, and that will impact how the current flows when the stimulation is applied. And those are the 11 tissues, and in addition to the background, so we have 11. And then if we want to perform manual segmentation through how we actually get our ground truth, it takes 2 hours to use a combination of different software, such as SimpleWell, Head Recall, FreeSurfer, and some manual annotation to get those automatic maps for each tissue. And then we have to do 1 month training for one RA, and then they have to perform manual fine-tuning because there are quite a few mistakes in those manual, like in those automatic software on the market or free as available in like open source. Then each brain on average takes 20 hours to correct all the 11 masks. And we need to segment 379. And if we want to apply to real time, digital brain like a closed loop simulation and feedback for the stimulation, that won't be feasible or realistic. So this is our work led by my PhD student, Skylar Stoddard, and she built GRACE, which stands for General, Rapid, and Comprehensive Whole Head Tissue Segmentation. It's published this year in Imaging Neuroscience, and we use phase 3 clinical trial data of 379 old adults at risk of Alzheimer's disease and related dementia, and we use this swing unit transformer architecture with our collaborator from NVIDIA. And those are the 11 tissues. And then you can see that we actually put all those 3D whole head into 12 samples. For each head, we have 12 samples because there are 11 tissues plus a background. Black background, and at the middle there will be the actual tissue we want to predict. And then this is our outcome, where on the left is a ground truth, which takes 22 hours in total to segment. And on the right is our transformer-based automatic segmentation in only 3 seconds. And now you may wonder, how does this grace compare with other methods, which are already open source or people widely use? Then we compare comprehensively with the past widely used and even the most recent methods, such as charm, which also from the same software, synonyms with head recall. And green is our grace method. And this is dice, which is higher the better. And you can see for almost all the tissues, our method is the best and most stable. And this is Hausdorff distance, which is lower the better. And you can see while we are best or comparable to hard recall, you can see for soft tissue, which is usually the hardest part, and the white matter, we actually achieve the best performance as well for the bone. And those are the challenging tissues because soft tissue and the bones take a smaller proportion of all the tissue voxels, and it has less data to train. And then we also want to look at the qualitative results. The first row is a ground truth, which we call reference, and the second row is grace. The third row is UNAT, which is a simplified, like a transformer-based UNAT directly segmentation without the transformer. And then we compare with charm, head recall, multiplier, SPM12, and ForkNet, which is also deep learning-based method in ForkNet. And you can see that for all those tissues, our method significantly outperform all the baseline methods. And UNet is the second best, but still in the details, we show in our results, for example, here, we have much better segmentation for those like blood, which is really hard. And here is a demo. Because of the transmission time, it's a little bit slower than actual processing time in batch in our computer. But you can see how in the future, we already have this web interface that will be public or available for users who request. We can just upload the Nifty file, and then it takes a little bit of time to process it. This is the longest part, which is the window inference. And now we have the results just in a few seconds. And you can see the whole head segmentation in 3-dimensional. Okay, good. And in addition to building this fast individualized segmentation, we are not like already satisfied with it because we also want to make our segmentation trustworthy and robust. And what does trustworthy mean? It actually has many meanings. And in this specific scenario, our trustworthy means a well-calibrated model, where calibration means the confidence output from the machine learning model actually matches the accuracy of this machine learning model in all the sample prediction. And we have published a series of work in MICAI in the past 3 years and also in journals about our trustworthy method, which we call Domino. So here is a more detailed introduction of calibration and trustworthiness. When we have a cohort of participants, if we can predict them at a certain confidence level from the neural network or from any machine learning classifier, such as support vector machine, random forest, they will usually output a confidence score. And this confidence score should tell the users, such as clinical doctors, how confident or how accurate this machine learning prediction is. For example, some of them have confidence at 10%, some at 20%, some at 90% or 100%. Then for those who are at 90%, we hope that when we apply this algorithm to all the participants who have 90% confidence, actually 90% of them are correct. So this is called well calibration. But not all the machine learning models are well calibrated. Usually they're poor calibrated because machine learning, or especially deep learning models, tend to be overconfident so that they can give a binary outcome easily. And here we design a new loss based on the relationships between the labels. And instead of using medical images, we use a more like a easily accessible everyday example. For example, we want to do the object recognition in the cityscape data set, which is the street scene. And we have a label of sign, a label of rider, and person. Then if we misclassify because our goal is trying to avoid hitting a person. So if we misclassify the person as a rider, there is smaller penalty because we should not hit either of them. And if we misclassify the person as a sign, there's a large penalty because we can probably hit a sign. It's not good, but it's lower harm than hidden person. But if we misclassify, probably there's a traffic accident in some emergency cases. So based on this concept, we design domino loss. And then here's our outcome. You see that this HC is hierarchical clustering and CM is confusion matrix-based domino loss, in addition to the regular loss like cross entropy loss, or the dice loss. And then you can see that quantitatively, we have better regional accuracy. And visually, we can also see better boundary detection. And more importantly, we have more calibrated results, which just means it's closer to the 45-degree line. Furthermore, in Domino++, we combine the hierarchical clustering loss with the confusion matrix loss, which details can be referred to our papers. It's a little bit mathematical in the original paper. Then we combine this expert-guided and data-guided regularization, and then use dynamic scaling and adaptive regularization weighting. And this Domino++ is an improved version of the first Domino, which are all of them are open source on GitHub. You can find them in our website. So when we test on the same site, noisy MR data, which means we train on site A and test on site A, but we add noise to the test data, you can see that the red line means there is a bad classification because the white matter and gray matter boundary is actually connected. But in our Domino and Domino++, they both are separated, like the ground truth. But also in the cancellous bone, you can see that we also perform much better. But the yellow boxes, you can see actually the Domino++ perform even better than the Domino. And here is test on the same side but rotated data. So you can see this is air muscle is a ground truth in those places, but it's misclassified as a cortical bone, which is like the yellow. And here in our Domino++, it's correctly classified. And furthermore, we train on side A and test on side B, which is train on UF side and test on Arizona side data. And then you can see the muscle, which like the gray in the ground truth is misclassified as bone, but in our Domino++, because it's good generalization ability to OOD data, which is out of distribution data, it actually can also classify well. This is very important for generalization and robustness of our like a whole head segmentation to different sites and different scanners data. Okay, after segmentation, we come to the volume measurement and finite element simulation to get a current density map. Usually people will use ROAST, which is an open source software from the University of New York, and it takes about 35 hours to simulate all the 71 lead fields. And then we can calculate the intensity and directions from those JMap, which is a current map. However, this is too time consuming if we want to build a digital twin at real time. So Skylar led this third work, which was accepted and presented at Mikai last year, where we build a direct mapping, which is a digital twin from the T1 MR directly to the JMap using a swing unit transformer to get the JMap, and then also an efficient net to predict or classify the electrode montage class to add this cross-entropy loss with the EC, which is calibration loss, and the data loss, which is MAE. And then by combining those three losses together, which you can see this is a reference, and this is a T1 input MRI image. And then when we gradually add different loss, we can get the best performance to be closest to the reference image. It is still have way to improve, but we are very encouraged to see that just by adding calibration and this classification to the MAE, we get a much better prediction of the JMF, like here for our like a real-time JMap prediction in this digital twin model. And after we have the JMap, which also takes 3 seconds actually, because it's a deep neural network inference, we perform machine learning classification for the treatment outcome and find out the signature centers to predict the treatment outcome. So this is our pilot work on a phase 2 clinical trial, and now we are validating it on our phase 3 data with over 300 participants. We have the brain and then T1 image tissue segmentation, finite element modeling to get a JMap, and then we input those JMap data to perform feature selection into a support vector machine, but this can be replaced by deep learning or any other transformers with larger data set. The reason why we choose SVM because of its robustness for this relatively smaller data set. And then we can get overall accuracy of 86% for the treatment outcome prediction. And what's more importantly is when we look at the highly ranked important regions from the SVM or machine learning prediction, we found those regions in the prefrontal cortices, such as the superior frontal gyrus and the middle frontal gyrus and the putamen, are the most important regions that will impact the treatment outcome. And this aligns with the literature and our understanding of how TDCS impacts the brain. And finally, after we can predict who will respond to this combined treatment, we can also try to turn the non-responders into responders, and that's the most exciting part. And we use multivariate Gaussian models to model the responders profile, and then use our precision dosing method to try all the different montages of the stimulation at different locations in the 1020 space and also different level of stimulation. And on this figure, you can see that the weighted root mean square error actually become much smaller after we use the optimized dose with the Hedges G effect size of over 3. And then you can also see that using this cosine map, the similarity between the optimized dose, participants which are non-responders before with the responders profile also increased significantly, especially in the prefrontal cortex. And furthermore, we also performed direct correlation, and the optimized non-responders, which should be responders now, and versus the responders mean, we can see a very high correlation of R squared equals 0.93. So this means in theory and in our digital simulation, we can change the non-responders to responders based on their specific head characteristics and anatomy. And a pilot trial has already been completed, and we are analyzing the data to see whether we can turn those real participants also into responders. Okay, I think because of time, I can now move to the second part, which is foundation models, a top-down approach. So what is foundation models? I think it's quite a buzzword right now after ChatGPT, which is a large language model, appeared in the end of 2022. So I think for those who know traditional machine learning, we know that we need training data, and then we have tasks, and then we also have the corresponding labels for supervised learning. So there's individual siloed models for different data, different tasks, and require task-specific training and lots of human supervised training. And we also have like traditional pre-trained model, if you have heard of those pre-trained models that you can download the weights, but they are mostly supervised fine-tuning. They need supervised fine-tuning to adjust specific downstream tasks so that they are not readily usable with zero-shot learning or few-shot learning. So foundation models is usually self-supervised learned model trained on massive amount of training data and can perform multitasks. And they can be adaptable within little or no training data. And also, they can just do inference in few-shot learning, zero-shot learning, or just prompt engineering to manage a wide variety of tasks with a singular model and their weights. So just like everyone's familiar with ChatGPT or with the other, for example, the DeepSeek, the recent most efficient model, you don't have to actually fine-tune it or teach it again for translation or for summary writing or for email writing because it's actually a multitask model already can be used off the shelf. And for medical data, a straightforward solution is actually we can employ a foundation model trained from natural images and then fine-tune it for different modalities of data. However, there's lack of public available quantity of annotations in the medical images. So we can also use this unsupervised learning method to train our foundation models. And then we can accelerate the development of accurate and robust models and also reduce the dependency on large amount of label data. And furthermore, we can preserve the privacy and confidentiality of patient data by using one coherent model that can be directly used for new size data. But we know that medical data is not similar to text or similar to our general daily like vision tasks because every region is quite different. Every organ, even every modality, and maybe every disease have a large image level variations, which can cause difficulties when training a unified foundation model. So that's why actually today we can see Nature publish one foundation model after one for pathology, radiology, oncology, and we just for example, in the department I'm visiting, Stanford Radiation Oncology, they just published another Nature paper on like like a vision language model for oncology. So I think it's still unanswered question whether we can train a unified, multitask, multi-organ, multi-modality foundation model for medical data. But we are on our path towards it. So this is a recently fresh off the press survey paper from our lab published in IEEE reviews in biomedical engineering. And we surveyed the recent 5 years foundation models in medicine and healthcare. And we found that they grow in parameter size, they grow in training size, but not always. And the omics is actually still an underdeveloped area, which can be further, needs further research. And when we look at what are the base models used to develop those medical foundation models, you can see that for language, BERT and Megatron are the mainstream. And then for images, actually this SAM-based model is very popular for segmentation. And then for the multimodal, like vision language models, clip-based is like the majority-based model. And this is a fast evolving field. And maybe every week or every month, we have new foundation models. So we are very excited about its future prospect. And I want to talk a little bit about our own foundation model. This is a gated brain project where we use UK Biobank and now also using the UF medical data to build a foundation model for the brain. there are multimodalities in the UK Biobank, which we start with, and we use Swing U-Net Transformer as our base model to train this foundation model. And this is published in Medical Image Analysis this year, and where we use 500,000 UK Biobank participants who have T1 and T2, and after excluding those who don't have both, we got 82,000 volumes from 82,000 participants. And we perform a three-stage training, where we first have the UK Biobank self-supervised pre-training, and then we assemble the target data sets and to have the target self-supervised pre-training, and then the target supervised fine-tuning and on the testing. So here's the results on Brett's Challenge 2021 tumor segmentation, where the top two green, orange are our model, which are self-supervised using the pre-trained model using SSL, and below are the supervised learning model. And you can see we outperform them on the performance. And more importantly is when we only use one modality to test, we train on two modalities, and when you use one modality to test, our model also outperforms significantly compared to the other models. And when we use few-shot learning, where we reduce the number of data in the input data for training, you can see that our model have a better performance compared to Swing U-Net Transformer, which is fully supervised learning. And finally, I want to briefly talk about equitable AI research in our lab, which was published in NPJ Digital Medicine. This is looking at women's health, trying to look at what is the current status of fairness for ethnic disparity in BV diagnosis for those asymptomatic BV bacteria vaginosis. And we use 16S RNA data, and this is collaboration with my wonderful colleague, Dr. Parker. And we found that there is a very significant difference between the false positive rate and false negative rate among the different ethnicity, where you can see that the Hispanic usually have a higher false positive rate, and the Asian have higher false negative rate. And using this method, we actually also train and test different ethnicity. So we train on one ethnicity and test on other, or we actually train on all the ethnicity and test on each. And we found that each ethnicity have their different signature bacteria. And using this method, actually, we identified novel bacteria, important bacteria, because they were usually neglected in the literature, even though some of them are already well reported. And this is an approach where we can identify whether there is disparity and also see for different ethnic background, whether the different bacteria play a significant role in identifying or early or diagnosis of this asymptomatic BV. Okay, and vision forward. So effectively integrating multimodality healthcare data will pave the path for trustworthy and precision AI in medicine. And this is what we are working on. We're not only focusing on multimodal imaging data, but also with electronic health records and clinical notes. And furthermore, the evolution of AI is a very interesting path, where we can see that when I was a PhD student in the first few years, it's rule-based, where we want to use math and expert knowledge to perform mathematical optimization to find the best segmentation or detection or image restoration. But when I'm closing to my PhD graduation and during the start of my assistant professorship, it becomes more data-driven. So everything is more machine learning, and we want to use data to mine the rules. But today, it's more foundation model prompting, because all those existing machine learning methods, as we said before, it's really more like a task specific and needs a lot of label to do human supervised and human, like we also need a lot of human involvement to design the training and task. So if we can build foundation models which are already available for example, task and like of clinical task and text data, and also for some of the imaging data, we can actually use prompting or prompt engineering to perform like interesting researches to understand, to test hypotheses and have very helpful clinical applications. So this is how the landscape of AI is evolving. And I think the foundation models is not only transforming AI by having higher performance and faster inference and no need for the trained like label data, but also it's democratizing AI because today maybe people with only a little bit of training of coding or even no training of coding can code with the help of those foundation models and know the pipeline, know how to write code or debug code. So I think this is good for the education of people from our background. So finally, in conclusion, digital twin builds a bottom-up emulation of the multimodal representation of the dynamic human body, and foundation models offers a top-down zero-shot, few-shot learning model for multimodal medical tasks. And combining both can chart a path for precision and generalizable brain health solutions. And this is also the future task for our lab. And here I want to acknowledge and thank all my lab members who have made all those research not only exciting, but also fun. And also my collaborators and the funding agencies for making all those research possible. Thank you so much for your attention, and this is my contact information.
Thank you. Excellent and greatly appreciated. We have a few minutes for questions and I think answers if anyone has any. If so, can I invite you just to unmute yourself to ask the question? Maybe while people are gathering themselves, let me just ask you, because my area is not neuroscience, but TDCS, obviously you were focused on models that sort of enhance therapeutic effectiveness for that, but what other applications would your models and approach have for other kinds of brain interventions?
Thank you, Daniel, for the excellent question, because our application of this digital brain twin is not only limited to TDCS or limited to agent or ADRD, it can be applied to other intervention methods such as TMS or TACS, as long as they involve the, for example, electrical or magnetic interaction with the brain. And also for diseases, it can be for any kind of disease, right, that have shown to be potentially effective using those intervention methods, such as mental health disease like anxiety and depression, which already TDCS have like a few published papers from Pruno on how they can be effective. And this is what we are working on right now, trying to see if this digital twin can help us to predict the treatment outcome better. And also, there's always heterogeneity in the treatment outcome. So we want to, like, without really putting the participant to different types of intervention parameters, we can see for a new participant with such a head anatomy and all the characteristics, we can know what is the best stimulation strategy. And also schizophrenia and other, like there's a number of, even Parkinson's disease. So there's a number of disease conditions that have shown, like TDCS have shown promise for.
Excellent, thank you. Other thoughts or questions from participants? I'm tempted to ask Andreas because I know that this is a domain that you have expertise in, for your thoughts and response if you're with us.
Hey, yeah, thanks so much. Thanks for the great talk. Really interesting. You touched on a number of different interesting issues, I think. I'm still sort of processing the part about foundation models, which I'm constantly thinking about and how to make them more effective. I'm just by way of background, I'm also a clinical neuroradiologist, and then I, work on AI applied to brain MRI. I think one of the big issues we run into is just the vast heterogeneity of clinical data, especially like truly clinical data that's acquired in the clinical setting. And maybe that's reflected in, you showed the UK Biobank data. You had to whittle the participants down where you're left with, a small fraction of the participants that have the sort of inclusion criteria that you need. And so how do you, I guess I'm curious, like how you think about that in the context of training foundation models. What ideally, I think you'd throw all the data at a model, but I think Nobi has been really successful at training successful models, at least in part because of that just vast heterogeneity, which I think you also highlighted.
Yeah, that's a wonderful question and very practical. So for UK Biobank, I think I can provide a little bit information. The reason why we went down from 500,000 to 82,000 is because not everyone has neuroimaging. So for all those who has neuroimaging, which is 44,000 and 43,000, most of them are included. And those are the people who don't have the neuroimaging. So I think as long as the person has the data we require, it won't be too much a problem, even though they are heterogeneous. Because the goal of foundation models is actually to take all the diverse data set into its learning process, which will actually help it to learn this manifold or distribution of the parameter space. So I will not worry too much about the heterogeneity of data, but outliers or hallucinations are actually real problems for foundation models. And I think this is still emerging on ongoing research challenges too.
Great.
Does that answer your question?
Yeah, any other questions? Please feel free to raise your hand or unmute yourself. And if not, let me just extend great thanks to you, Ruogu, on behalf of all of us. And yeah, looking forward to seeing. I will bracket that the women's health piece seemed kind of separate and apart, but we have a number of colleagues in a cross-campus affinity group who are working on AI and ML and women's health. And so I may reach out to you to connect you and them for that piece, which is kind of apart from the brain work, but also of interest. Yeah, great thanks to you, and look forward to seeing where this takes you. And we will refrain from circulating slides 47 and 48 on unpublished work, but look forward to reading about it when it is published. And
thank you so much, Daniel. And
thanks to all for
everyone.
coming.
Thanks, Yao.
Bye for now, everyone.
Bye. Great to see you, Dr. Fang.